It's funny how we look at real estate. You walk into an open house in one of those really charming, established neighborhoods, right?
Absolutely.
Like maybe a place built 30 or 40 years ago. You see the fresh coat of greige paint, the staged mid-century furniture. Maybe they've slapped some gleaming quartz countertops in the kitchen.
Right, the stuff that looks good on a listing.
Exactly. You look at all that cosmetic surface and think, wow, perfect. This house is completely turnkey.
Hmm.
But then you actually buy it, you move in, and you realize you completely ignored the actual engine of the house,
Yeah, the stuff you can't see.
right? The hidden infrastructure.
Yeah.
I mean, we are talking about the home's central nervous system today,
Yeah.
the electrical grid running right behind that fresh drywall.
It really is the ultimate blind spot for most homeowners. I mean, we expect electricity to be this invisible, infinite resource. You flip a switch, the lights come on.
Yeah, it's basically magic to most of us.
Right, but the physical reality of how that power is delivered and, well, the physical degradation of the materials carrying it is completely ignored until something catastrophic happens.
Which brings us to today's deep dive. We are working through this massive stack of case studies, technical guides, and articles from Burleson AT Electric.
Yeah, they're a specialized local contractor down in Texas.
Right, specifically operating in the DFW area, Johnson and Tarrant counties. And our mission today is to sort of pull back the drywall on this hidden nervous system. Because looking at this data, there is this incredible structural conflict happening right now in neighborhoods across the country.
Like a huge issue, yeah.
You have the undeniable charm of these older homes colliding head-on with the massive, relentless power demands of our highly connected modern lifestyles.
It is a really fascinating structural bottleneck. You've got infrastructure designed for the analog era, basically being asked to power the digital era.
Yeah, which is a tall order.
It really is. So my goal today is to look at the mechanics of this, to bridge that gap between aging, deteriorating infrastructure, and modern electrical physics, and, explain why proactive maintenance is really the only way to avoid a disaster.
Okay, let's unpack this because I want to get away from the basic surface level stuff. I mean, we all know that if you run a vacuum and a space heater at the same time and the breaker trips, you've overloaded the circuit.
Right, that's basic homeowner stuff.
Yeah, exactly. But what this documentation from Burleson AT Electric gets into is the actual decay of the materials inside the walls over decades. It's like human arteries almost.
That's a great way to think about it.
If I'm living in a house built in the 70s or 80s, I don't just have quote-unquote old wires. I have entirely different materials than what we use today, right? Could you walk us through the warning signs of a system that's essentially failing?
Absolutely. The building materials themselves are often the primary liability, and you'll see physical symptoms, things like flickering or dimming lights, frequently tripped breakers, warm switches.
Wait, warm switches, like physically warm to the touch.
Yeah, exactly. Or you might hear buzzing coming from the walls, see discolored outlets, or even catch burning smells.
That is terrifying.
It is. Take aluminum wiring, for example. During the copper shortages in the 60s and 70s, builders pivoted to using aluminum for standard residential branch wiring. At the time, well, it seemed like a cost-effective alternative, but what we know now about the metallurgy is just terrifying.
I always thought aluminum was just a cheaper conductor. Like, why is it actually dangerous inside a wall?
It really comes down to thermal expansion. When electricity flows through a wire, the electrical resistance naturally generates heat.
Okay, makes sense.
And aluminum expands and contracts at a significantly different rate than copper when it heats up and cools down. So every time you turn on a heavy appliance, that aluminum wire at the connection point, say, right behind a wall outlet, it gets warm and expands.
And then when you turn it off...
When you turn the appliance off, it cools and contracts.
So it's essentially wiggling itself loose over time. Like taking a paperclip and bending it back and forth over and over again.
That is the perfect analogy, yeah. And eventually, that expansion and contraction creates this microscopic gap between the wire and the screw terminal holding it.
And a gap is bad news, I assume.
Very bad. In the electrical world, a gap means the electricity has to jump or arc across the space to keep flowing. That micro-arcing creates intense, localized heat. I mean, easily enough to melt the surrounding plastic insulation and ignite the wooden studs in your walls.
And the scary part is, you can't see this paperclip effect happening. It's entirely enclosed in a plastic box behind drywall.
Exactly. And the other major historical liability we see in these older homes is outdated panel architecture. There are specific discontinued brands of electrical panels still sitting in thousands of homes today.
Like which ones?
Brands like Federal Pacific or Zinsco, they are absolutely notorious in the industry for a fatal mechanical flaw. The breakers can physically fuse to the bus bar.
Meaning they lose their ability to actually trip and shut off the power.
Precisely. I mean, a breaker is a safety valve, right? If too much current is flowing, it's supposed to physically snap open and kill the circuit.
Right.
But if it fuses to the metal bar inside the panel, it just keeps letting current flow no matter how much the wires are overheating.
Wow. And this makes me think about the whole DIY culture we have today. You look up a 5-minute video on YouTube and think, oh, I can swap out a buzzing outlet or change a breaker. How hard could it be?
Oh, people do it all the time.
Right. But reading through the building codes here, doing unlicensed electrical work isn't just about the immediate risk of, shocking yourself. If you try to put a Band-Aid on a degraded aluminum connection, and you don't use the exact specialized connectors required by the National Electrical Code, you are practically guaranteeing an electrical fire.
And compounding that risk is the financial fallout. If an investigator determines that an electrical fire started from amateur, unlicensed modifications, it can entirely void your homeowner's insurance policy.
Oh, wow. So you're entirely on the hook for it.
Yeah, you are taking on catastrophic financial and legal liability, potentially hundreds of thousands of dollars, all to save a couple of $100 on a professional contractor.
It's just not worth it.
Not at all. I mean, you wouldn't perform DIY surgery on your own spine, but people routinely attempt DIY surgery on their home's nervous system.
Right. That's a really stark way to put it.
Huh.
And knowing the mechanics of how these older systems fail really sets the stage for the next problem. Because it's not just that the wires are degrading in a vacuum, it's that we're demanding these compromised 30-year-old systems to handle loads they were never engineered to support.
Oh, absolutely. The metabolism of a modern home is entirely different.
What's fascinating here is just the sheer volume of power we draw today. A house in 1985 had, what, a refrigerator, a tube TV, maybe a microwave?
Pretty much.
Today, look around your living room. You have smart appliances constantly pulling data, dual monitor home offices, massive HVAC systems, automated lighting.
And all of that, I mean, it really pales in comparison to the elephant in the room.
The electric vehicle.
Exactly.
Wait, if I buy an electric vehicle, can't I just plug it into the standard garage wall outlet overnight? I hear this argument all the time from people who are hesitant to upgrade their homes. They say, I have an outlet in my garage, I'm just going to plug it in overnight like my smartphone.
I hear that constantly too. But looking at the load calculations here, treating a car like a smartphone is just a recipe for a house fire.
Because it's just too much power at once.
It absolutely is. And it comes down to understanding the physics of a continuous electrical load versus an intermittent load.
Okay, what's the difference?
Well, when you plug in a high-draw appliance like a hairdryer or a toaster, it demands a massive amount of amperage. But it only does so for maybe 3 to 5 minutes.
Right, you make your toast and it's done.
Exactly. The wires in the wall barely have time to get warm before the device shuts off and the thermal stress dissipates.
But an EV charger doesn't shut off in 5 minutes.
Right, not at all. An electric vehicle charger draws that heavy maximum electrical load continuously for 8 to 12 hours straight.
Wow, okay.
A standard 15-amp garage circuit wired with standard 14-gauge wire was never, ever designed to endure that kind of sustained thermal stress. The wires will literally bake inside their insulation until the plastic melts away.
Exposing bare copper to the wood framing.
Exactly.
So, mechanically speaking, how does a professional EV setup solve that thermal problem? What is a level 2 charger actually doing differently?
Well, a level 2 charging station jumps the voltage from a standard 120 volts up to 240 volts. It's very similar to an electric oven or a clothes dryer.
Which is why it charges so much faster.
Yeah. But to handle that kind of voltage and amperage, usually 40 to 60 amps safely, you need a dedicated circuit.
Dedicated meaning a single, uninterrupted run of wire straight from the charger back to the main breaker panel, with nothing else sharing the load.
Exactly. And more importantly, it requires much thicker gauge copper wiring that can handle that continuous heavy current without overheating.
Makes sense.
The real bottleneck, though, is that most older homes with 100-amp main panels simply do not have the physical capacity to add a 60-amp dedicated circuit just for a car. not on top of the air conditioning and the kitchen appliances.
Which means you are looking at a full panel upgrade, ripping out the old 100 amp box and installing a modernized 200 amp main panel.
Yes, exactly.
And I think a lot of people balk at that because it sounds like a massive week-long renovation project. But the data from Burleson AT Electric actually notes that a specialized local crew typically completes a panel upgrade and an EV charger installation in about 4 to 8 hours.
Yeah, it's a very streamlined process for experienced contractors, and honestly, the peace of mind is immeasurable. You are fundamentally expanding the electrical bandwidth of your entire property.
Okay, so we've established that our internal demand, like our EVs or home offices, is stressing the grid from the inside.
Right.
But I want to shift gears slightly, because if you have an EV and your home is totally electrified, your entire life is basically tethered to the stability of the grid. And in Texas, the grid is anything but stable.
That is so true. If we connect this to the bigger picture, this raises a really important question about geographical context and local expertise. The infrastructure in the DFW area faces severe environmental stress testing.
I mean, you have sweltering Texas summers where millions of residential air conditioning units are running simultaneously at maximum capacity.
Yeah. And that constant, massive draw causes the utility grid to fluctuate, right? You get rolling brownouts or sudden drops in voltage.
And people often underestimate voltage drops, don't they? They think surges are the only real danger.
They absolutely do. But when a motor like the compressor in your AC unit or your refrigerator doesn't get enough voltage during a brownout, it tries to compensate by drawing more amperage to do the same amount of work.
Oh, I see.
And that excess amperage generates immense heat, which just degrades the motor's internal windings.
So it essentially slowly cooks the appliances from the inside out.
Precisely. And then on the flip side of the weather spectrum, you have the severe Texas thunderstorms.
Right, the lightning.
Yeah, a lightning strike or a grid malfunction sends a massive spike of voltage down the utility lines directly into your home. A modern home is just filled with microprocessors.
Yeah, even the fridge has a computer in it now.
Exactly. The stove has a motherboard. The washing machine has a logic board. A single high-voltage surge can fry thousands of dollars of sensitive electronics in a microsecond.
Which is why whole home surge protection is emphasized so heavily in these guides. It takes, what, a few hours to install?
Usually about 2 to 4 hours, yeah.
But I want to clarify how these actually work, because I always sort of assumed a surge protector was just a heavy-duty power strip that clicked off if things got crazy. But a whole home unit installed at the main panel operates completely differently, doesn't it?
It does, yeah. It operates on a component called a metal oxide varistor, or an MOV for short.
Right, an MOV.
You can think of an MOV as a pressure relief valve for electricity. Under normal voltage, the MOV does nothing. It just lets the power flow into your house. But the instant it detects a massive spike in voltage, its internal resistance drops to 0.
So it creates an immediate detour.
Exactly. It instantly shunts all that destructive excess voltage away from your home's circuits and dumps it directly into the earth via your home's grounding system.
Oh, wow.
Yeah, the MOV basically sacrifices its own lifespan to absorb that hit, saving your electronics in the process.
But that detour only works if the ground it's dumping the electricity into is actually receptive, right? The materials mention how crucial it is for local contractors to understand soil conditions for grounding rods. Why does the dirt around my house matter to my electrical panel?
It's just a matter of basic chemistry and physics. A grounding rod is a long copper or galvanized steel pole driven deep into the earth. For electricity to flow safely from that rod into the ground, the soil needs to be conductive.
Okay, so moisture is good.
Yes, water-containing dissolved ions is a great conductor. But bone-dry, sandy soil, or that hard-baked clay during a Texas drought essentially acts as an insulator.
So if the soil is too dry, the surge has nowhere to go, and it bounces back into the house anyway.
Exactly right. The path of least resistance just becomes your home's wiring instead of the earth.
That is wild.
This is why a regional expert understands the local geology. They know if they need to drive the rods deeper to hit moisture, or if they need to use specialized grounding plates based on the specific clay composition in, say, Tarrant or Johnson counties.
That's fascinating. It really highlights why you can't just hire a generic handyman for this stuff. You need someone who knows the physical DNA of the region.
Absolutely.
And speaking of fighting the environment, another structural defense they detail here is burying the power lines entirely, moving them underground. Now, my first thought is, digging up a yard to lay PVC conduit sounds like an expensive landscaping nightmare. Why go through that effort when the overhead lines seem to work fine?
Well, overhead lines work fine right up until they don't. Moving power lines below grade into durable, sealed PVC conduit provides an incredibly robust physical armor for your connection to the grid.
Because it's out of the weather.
Yes. In Texas, you are dealing with high wind events, sudden ice storms that accumulate weight on the lines, falling tree branches, burrowing wildlife, severe lightning.
So instead of your main power feed swinging in the wind, vulnerable to every storm that rolls through, it's sitting in this subterranean fortress.
Yes. The data shows that properties with underground connections experience a fraction of the service interruptions compared to those with overhead lines.
And I'll add a purely aesthetic point here, which matters if you ever plan to sell. Removing those thick, draping black cables from your sightline instantly cleans up the sky above your property. It drastically elevates the curb appeal.
It really is a functional upgrade that yields an immediate aesthetic return.
Okay, we've talked about upgrading the panel for heavy loads, and we've armored the house against the grid and the weather. Here's where it gets really interesting, because the electrical system isn't just about protecting appliances. It's about adapting the architecture of the house to protect the people living inside it.
That is a very important point.
Especially when we look at the demographics of these older, charming neighborhoods.
That's a critical shift in perspective, yeah. A house is a static structure, but the people living in it are dynamic. The demographics show a massive foundational pillar of retirees and the 55-plus community wanting to stay in these established neighborhoods.
Right, this is the concept of aging in place.
Exactly.
People don't want to be forced out of a home they've lived in for 30 years just because their mobility changes. But adapting a house for aging in place isn't just about installing grab bars in the shower. The electrical infrastructure plays a massive role in accessibility, particularly regarding visibility and preventing falls.
Falls in transition areas like hallways, staircases, and bathrooms are one of the highest risk factors for older adults. As eyes age, the pupil gets smaller and the lens thickens.
Meaning they just let in less light.
Right, meaning an older person needs significantly more light to see the same level of detail as a younger person. Furthermore, their eyes take much longer to adjust to sudden changes in brightness.
So the old solution of just, putting a 100-watt bulb in a hallway fixture actually makes things worse because it creates harsh glare and deep shadows.
Exactly. The architectural retrofits recommended by Burleson AT Electric focus on strategic, high-lumen, energy-efficient LED lighting.
High lumen, meaning very bright but smooth.
Yes, providing a smooth, even wash of light that eliminates harsh shadows and helps aging eyes easily distinguish contrast, like the edge of a step.
And they pair this heavily with motion sensor technology, which makes so much sense when you think about the friction of daily routines.
It removes the vulnerability entirely. An older adult waking up at 2 in the morning shouldn't have to navigate a dark hallway, waving their hand against a wall to find a switch.
Right, hoping they don't trip over something.
Exactly. With automated transition lighting, the house anticipates their movement. The path illuminates gently as they walk and turns off behind them.
That's brilliant. And for the switches they do need to interact with, swapping out those tiny traditional toggle switches for wide, flat rocker switches is a game changer for anyone dealing with arthritis or declining hand dexterity.
It's a huge help.
You don't have to pinch and flip. You can just tap it with your palm or your elbow.
It's all about designing a frictionless environment. We also look at the placement and accessibility of the main breaker panel itself. In many older homes, the panel is installed awkwardly high on a wall or shoved in the back of a dark utility closet.
Which is terrifying if the power goes out and someone with limited mobility is fumbling with a flashlight, trying to read faded, handwritten labels from 1988 to figure out which breaker goes to the medical equipment.
That is exactly the scenario you want to avoid. Relocating a panel to an accessible height, often wheelchair accessible, and ensuring the main breaker is clearly labeled in large, high-contrast text transforms a stressful emergency into an easily manageable situation.
Now, I can hear a listener thinking, this sounds like a total gut renovation of my house. But looking at the project timelines provided, retrofitting a home with automated accessibility lighting and rocker switches is typically just a 1 to 2 day project for a professional crew. It's incredibly localized work.
It is, yeah. It is a high-impact, low-disruption upgrade. You aren't knocking down walls. You are simply updating the interface points of the nervous system.
So what does this all mean? We've covered a massive amount of ground today.
We really have.
We started with the microscopic physics of aluminum wires creating hidden fire hazards, moved through the heavy thermal demands of level 2 EV charging, explored how MOVs and grounding rods defend against Texas weather, and finally looked at architectural lighting for aging in place. How do we synthesize this for someone walking around their 1980s home right now?
I think if we pull all these threads together, the singular takeaway is that electrical infrastructure is not static. It degrades, and the demands we place on it are accelerating rapidly.
It's not just flip a switch and forget it.
No. The overarching lesson is that proactive maintenance is mathematically cheaper and infinitely safer than reactive emergency repairs. You do not wait for a wire to start melting to alert you to a thermal bottleneck.
Right, you don't wait for the engine to seize up before you check the oil. The documentation gives a very clear, actionable golden rule, actually. Schedule a comprehensive professional electrical inspection every 3 to 5 years, or, crucially, immediately before you close on a new home.
Yes, that is vital.
That is the only way a specialist can get behind the drywall, catch loose connections and degrading insulation early, and catch a failing panel before it costs you the house.
It is the ultimate form of preventative structural medicine.
It really is. It all comes back to looking past the aesthetic surface, which leaves you with something to ponder the next time you are browsing real estate listings, admiring those beautiful, fresh renovations. As we move into an era where our vehicles, our heating systems, our daily tools become entirely reliant on electricity, will the true real estate value of a home soon be measured not by its square footage or its aesthetics, but entirely by the invisible capacity of its electrical panel?